So thank you very much. I want to thank especially Denis for doing such a beautiful job before lunch, because I hope I will be able to connect it to what I will do now. So yesterday we talked about a certain construction of the universal cover of a p-divisible group, and which was simply the group functor that associated the inverse limit under multiplication by p of Gs to any ring S. It associated this inverse limit. And I said that this was a crystal. And Grothendieck has a very nice saying that crystals are rigid and they grow. In what sense? So without making a formal definition of crystal, what did it mean in that context? It meant that if we have a nilpotent thickening, so if we have S goes to R, rings where the kernel of this homomorphism is nilpotent, or maybe pro-nilpotent in the topological setup, then the universal covering, and you have a group over S and R compatible with reduction, and the universal cover of that group, its S point and its R points are just the same. And in particular, it doesn't depend on the group over S, but only on the group over S mod I, which was R. Okay, so no matter how you deform the group, you got the same result. We're going to encounter now a second crystal, which is the Grothendieck-Messing crystal, or the Dieudonné crystal. It will be a little bit more complicated in two respects. First of all, it will require not only nilpotent thickenings, but nilpotent thickenings with divided power structure. And we've already seen divided powers appear in several circumstances, and they will become more and more important, I think. The second thing is that it is not going to be a crystal in groups, but it is going to be in crystal of O modules. So you will not expect the thing to be the same, but you expect, because you want an S module and an R module, right? But you expect somehow the S module to reduce to the R module. So it will be a little bit more complicated, but okay. Now to define it, we should start with the notion of universal vectorial extension. And I remarked before that it's very good to look at p-divisible groups as sheaves for the FPPF topology, and we didn't take it very seriously until now. What does this mean? It means simply that there are functors. If they're defined over R, there are functors on R algebras, or if you want affine R schemes, or you can do it any R schemes. And so that just means that they're pre-sheaves, but they satisfy the usual sheaf axiom with respect to a family of cover rings that in this case we take faithfully flat of finite presentation, which is a rather large and useful family of coverings to work with. But this abelian of FPPF sheaves is an abelian, this category is an abelian category, and therefore we can apply homological algebra. So look at the exact sequence G p to the n to G multiplication by p to the n onto G. So it's onto exactly because G is p-divisible. And if you look at the long exact sequence associated to it, you get, you first hom into GA, and then you take the long exact sequence, then you get hom G to GA over p to the n of hom G to GA, right? Then it goes into hom GP to the n GA. It's contravariant, so it goes backwards. And then the first derived functor will be x G by GA, the X1 group, and there will be this map p to the n, so it will be onto the kernel of p to the n. So if you're familiar with descent sequence on elliptic curves, this is formally, of course it's not the same, but it's formally the same kind of construction. Now what can we say? The first term is 0 because G is p-divisible, but we now assume that p to the n, as usual, kills the ring R. Later on we will pass to the limit. It will still be 0, but you can assume for the moment that some high power of p kills R. So this immediately tells you that there are no homomorphisms from G to GA. Now, how about the last term? The last term, again, is an R module, and if little n is greater than or equal to big N, then everything is killed by P to the N. So no homomorphisms of formal groups or of group of, actually, G need not be formal and GA is not P divisible, but as FPPF sheaves, right. So, but here you do, of course, use the fact that G is P divisible. There are homomorphisms from GA to GA, right. And so what you get is that the extensions of G by GA are simply the homomorphisms from the P to the N torsion on G to GA, if little n is big enough. And if you work it out in terms of the Hopf algebra of GP to the N, which we call AN, right? So such a homomorphism is determined by where X, the coordinate on GA, goes. So it goes to a number that we call A, and that number should satisfy this co-multiplication of A is A tensor 1 plus 1 tensor A. Such elements are sometimes called primitive, but it has nothing to do with the notion of primitivity that was introduced before. And then if you pass to the dual point of view, and you view AN as functionals on the dual Hopf algebra, then this is nothing but the familiar rule of differentiation. So this becomes a derivation centered at the origin because of this one, becomes the unit section in the dual P divisible group, and this is therefore the Lie algebra of the dual, and for n large enough, we said that this stabilizes, and this is therefore the Lie algebra of the dual P divisible group, which is the homomorphisms from the cotangent space at the origin of the dual P divisible group to R. So what did we finally prove here? And this is a full proof of the fact that the extensions under these conditions are represented by, right, as a functor on R, are represented by omega G hat. And the same thing works if you replace GA by any vector group. Vector group is just finite number of GAs, that's all. Okay, so it's just a module, a fixed module, R module, tensored with GA. I put a line under it to say that now it's a group functor, not just a module in the sense of ordinary modules. So we get this very nice identity between extensions of G by any vector group and homomorphisms from omega G hat to M. But now you can plug for M omega G hat, right? And then you have a distinguished homomorphism, the identity. So this distinguished homomorphism gives you a distinguished extension, which is the universal extension. So the extension EG of G by omega G hat as sheaves, okay, in this abelian category, is the one that corresponds to the identity when you take M equals omega G hat. And furthermore, any other extension, that's an easy exercise, is obtained by a push out of this exact sequence with respect to homomorphism from omega G hat to M. So if you have such a homomorphism for a general M, what is the thing that you get on the left? You get the push out of this diagram. So this is the whole theory of universal vectorial extension. And if we now apply the Lie functor, remember the Lie functor was defined for any group functor. It was the kernel of the group functor evaluated at the dual numbers over R to the group functor over R. So if we apply the Lie functor to this exact sequence, you get an exact sequence of vector groups that has the Lie algebra of the universal vectorial extension in the middle, Lie of G as a quotient, and the cotangent space of the dual as the subthing. And this is the Grothendieck-Messing crystal. It is, by definition, the Lie algebra of the universal vectorial extension of your P divisible group. We have not made it into a crystal yet, but so far it's defined for any R as an R module. So what can we say for any R algebra? Say S, MGS is a locally free module, right? It's an extension of locally free by locally free, whose rank is the dimension, the rank of Lie G, which is the dimension of G, plus the rank of omega G hat, which is the dimension of G hat, G dual rather, not hat, G dual, Cartier dual. But the dimensions add up, the dimension of G and the dimension of the Cartier dual add up to the height of G. Okay, in the case of an abelian variety, the height is twice the dimension, and because of the polarization, the two dimensions are the same. But in the case of one-dimensional group that we saw in Denis' talk, this was one-dimensional, this was, or would be H minus one dimensional, and this would be H dimensional. And our goal is to enhance Mg to a crystal of modules on the crystalline side. So I will explain exactly what this means, but to explain it and to sketch the proof, we need a notion of a rigidified extension of a group that now will be G dual by Ga. So given an extension of G by Ga, of course, it in general will not split, okay? It will not, the extension will not be the product of G by Ga, but we may be lucky and it may split on the level of Lie algebras. And splitting on the level of Lie algebras is often easy to obtain, and it simply means that this exact sequence of Lie algebras splits, and this would be called a rigidification. To give such a splitting, a map from Lie G back to Lie of the extension, so that if you go this way and back to Lie G, you get the identity, this is a rigidification. Now, if you have a rigidification, any other rigidification differs by what? By a homomorphism from here to here, of course, right? The difference of the two should vanish when you take this arrow, so it should be a homomorphism actually into here. And this is nothing by an element of omega, right? A homomorphism from Lie to Ga. So if you want to make, and you can make the set of rigidified extensions easily into a group by what's called a bare sum of extensions. It works also for rigidified extensions. It sits in an exact sequence like this. Every rigidified extension goes to the extension forgetting the rigidification, this splitting on the level of Lie algebras. It is surjective because of formal smoothness. You can always find such a splitting on the level of Lie algebras. And the kernel is omega G hat, or rather, every set of rigidifications is a principal homogeneous space over omega G hat. And we've already seen a way to identify these extensions with the Lie algebra of G. Remember, this was just what we did here. Whoops. Here, the extensions were identified with the Lie algebra, but of course, now I'm applying it with G hat and G interchanged. So we've already seen a way to identify these two. We've already, of course, this is the identity. There is a universal extension and its Lie algebra extension exact sequence here. So you can guess, and this would be perfectly good and easy to prove guess, that the rigidified extensions canonically can be identified with the Grothendieck crystal, with Mg of R. So just as the extensions were identified with the Lie algebra, the rigidified extensions are identified with the Lie algebra of the universal vectorial extension. And now I have to say something about the crystalline side. So this will be a side, meaning it will be a category, and in this category there will be a distinguished family of coverings, and it will be cooked up in such a way that it will be just the right category to discuss divided power thickenings. So it's going to be what's called a big crystalline site, in the sense that if we start with a ground ring R, then we first make an arbitrary extension of rings. Of course, if you were doing schemes, all the arrows would go in the opposite direction. Usually people do schemes. I chose to stick to affine schemes and describe it on the ring level. So an object is really a diagram like this. First you have a ring homomorphism from R to S, and then you have another ring homomorphism from T to S, but this one is required to be a nilpotent divided powers thickening. And this is a little bit technical. First of all, it is required to be a nilpotent thickening. This means that the kernel should be a nilpotent ideal in T. Furthermore, the kernel, this ideal I, kernel of T to S, should have divided powers, and the divided powers themselves should be nilpotent. Now, if S is ZP flat, this can be very easily defined. Okay, so this means that if X is in I, the kernel of T to S, then X to the n over n factorial, that is defined at least after you invert P, which is allowable because S is ZP flat, is also in I. And there is an extra condition on the nilpotency of the divided powers that I wrote here that implies that I is nilpotent but is stronger. If S is not ZP flat, you do not know what you mean by X to the n over n factorial. So, as usual, when we do not know what we mean by something, we make an extra definition, okay? So, in this case, the divided power structure will be an extra input. Usually it's denoted gamma n of X. And it will have to satisfy a long list of properties that are all derived from the usual properties of X to the n over n factorial. And you can find them in a book by Berthelot and August, for example, or in many other references. So these are the objects. Morphisms in this category are obvious maps between such two diagrams that commute with the divided power structures when you endow it. Yeah? Sorry?
T to S should that be surjective?
T to S is surjective. There is a little double arrow here. Maybe it's not. Yeah, maybe it's not clear. When I say thickening, I mean it's surjective with kernel I. Okay, there's a little double arrow here. Okay, yep. Now, what are the coverings? The coverings are very easy. The coverings are just the usual old coverings in Zariski topology, but of course on the level of T. So you want T to be covered by a family of TIs, Zariski open, and then the SIs will just be the reductions of the TIs, so to speak, okay, the fiber products. And this nice category has a structure sheaf which assigns to any such diagram, now to save space I just wrote T to S without the reference to the ground ring, the usual functions on T. And now comes the big theorem of Grothendieck and Messing. This was the PhD of Messing, that if you have such divided power nilpotent thickening, and if you lift G, so G started life on R, you can base change it to S, but then as we know by Lazar, it lifts in many ways to T, so choose one such lifting, call it G prime T, and calculate the Lie algebra of the universal vectorial extension of this lift. It's right, a locally free T module of rank H. But it depends functorially only on G. And for some reason I didn't get the last line of the slide. We will denote it by mg of T goes to S. So this will be the crystalline property of it. And what do we mean by it depends functorially only on G over S and not on the lift to T, we mean that if we take another lift, there will be a canonical identification of the two things. And furthermore, if we have a map between G1 and G2 on S, and if we take an arbitrary lift G1 prime and G2 prime of the two and calculate the two things, then this map between G1 and G2 on the level of S will induce a canonical map between these two mg prime t's calculated for whatever liftings we chose. So this is the very nice theorem, and as you see, compared to the universal covering, we have, first of all, to assume that this thickening is not just any nilpotent thickening, but a PD nilpotent thickening. And secondly, we cannot say that on the nose it gives you the same module, but it gives you a T module whose reduction is S in a canonical way. Okay, and when T is S, of course, you can take T equals S. That's a perfectly good thickening. We will simply drop S to S, and we will write mg of S. And I'm going to follow a very nice exposition of Nick Katz that was given here in India, but in Mumbai, at Tata in Mumbai, 40-something years ago, that will A, connect it to what Denis did, B, sorry?
Most people were not born at that time.
Ah, but you were. Okay, but maybe you were not present there. Okay, it A, connects it to what Denis did, or rather Denis looked at my slides and built his lectures so that it will be related. B, it shows how the PD, this explanation shows how the PD structure comes into the game. And C, it connects things to the RAM cohomology and differential forms. So unfortunately, it works under some assumptions, especially the assumption that everything is ZP flat, no P torsion. So far, we were assuming that P to the n is 0, so I'm skipping a step of going to the inverse limit over P to the n, and from now on, we will assume that the thing is ZP flat. So we start with really the same thing that was here before lunch, and we will also assume that our P divisible group is formal, just as Denis said when he was explaining Colmet's construction. It makes life easier. Okay, but that Katz does it too. So if you want to see all the generalities, you have to go and study Messing's thesis, which is a long, fat book, which I haven't done, but some people have done it. The RAM cohomology of the formal group F over R will be those cohomology classes. So first of all, F is just, without the group structure, it's just the formal spectrum of power series ring in D variables, so it's clear what we mean by differentials, right? We mean F1 dx1 plus F2 dx2, et cetera, plus Fd dxd, where the Fi's are power series themselves. Now, this has nothing to do with the group structure. But there is a notion of being closed or exact, of course, as usual in power series. So we look at the classes of closed forms modulo exact, such that the pullback of that form under the co-multiplication, okay, so that would be now a differential form in x1 up to xd and y1 up to yd. Denis treated the y's as constants, but here I want to treat the y's as variables. Minus eta tensor 1 in the x's, minus 1 tensor eta in the y's is exact. So this means that maybe not the form on the nose is translation invariant, but the class is translation invariant. Fine. Now we can also talk about the really translation invariant differential forms. So this was a one-dimensional space in the example before lunch spent by this omega 0, for which in the one-dimensional case we could give a very nice description in terms of power series. Okay, so these are, and of course if the form is translation invariant, its class is translation invariant, so there is a map, but the map, the thing to observe is that the map is injective because R is p-adic and F is p-divisible, right? If you have something that is both translation invariant and exact, then it's primitive in the sense of calculus, would be a logarithm, but logarithms for p-divisible groups require p's in the denominators. Okay, there are no homomorphisms from a p-divisible group to GA over a base in which p is nilpotent or topologically nilpotent, other than 0. So now we have this exact sequence that used to define the crystal. We have this exact sequence that we saw is identical with this, if you believe me, that the rigidified extensions are the Lie algebra of the universal vectorial extension. And now I'm going to relate it to a third exact sequence in the following way. Well, this exact sequence will have omega, H1 de Rham, and this will be the Hodge filtration in here, and the quotient I will describe as a certain cohomology group, which I will define in a moment. This cohomology group will be very easily, or by well-known techniques, identifiable with the extensions. And once again, the middle term will have no choice but to get identified with the rigidified extensions. So we will have this identification through the rigidified extensions between what we want to study and the Rham cohomology as appeared before lunch. So what I owe you is an explanation of this and the map delta. And here it is on the level of power series. We look at all, so for simplicity, let's assume that we're in the one-dimensional case. We look at all the power series in 2D, or two variables in this case, that are symmetric under change of x and y, and satisfy this relation, this cocycle relation. With the cocycle of a power series like this is a power series in 3 sets of variables now, and it will be delta of yz minus delta of x plus y on the formal group, right? Add these two variables under the formal group law. Z minus delta of x y plus delta of x y plus z minus delta of xy. And you divide, so this is a huge abelian group of power series, and you divide by all the ones that are obtained, that are coboundaries, that are obtained by delta from functions, or power series rather, of one variable. So if f is any power series of one variable, you look at fx plus y minus fx minus fy. So, right, this delta is, what is it? It's the obstruction for f to being a logarithm, right? It's the obstruction for f to obey f of x plus y on the formal group is f of x plus f of y. And it's very easy to check that anything of this sort satisfies that this is 0, and the quotient is this H2. The little s here refers to the symmetry condition. And the map from H1, this map that I called delta before, right here, this map that I called delta, is the following. You start with your class, which is translation invariant. You represent it by eta. This would be, in the case that Denis was discussing, this differential form of second kind, but in general, in the higher dimensional case, I think it's impossible to do this, or at least not known to me. And then you can integrate this eta formally, but you need denominators. So you integrate it, you get an f, and you take the delta of this f. Now, watch out. It will not be in the denominator, because the denominator is obtained from delta of f's, where f's are over r. But here, f is over r1 over p. Nevertheless, the delta of this f will have integral coefficients, and because it was obtained of as delta of something, maybe with denominators, it will be capital delta, whose class will lie in this H2. So this is the construction. And as I promised you, I will not go over the identification of these 3 exact sequences, but it's rather easy. And now comes the main lemma and I want to prove this lemma at least in one specific case so that you see what goes into it. So we have such a formal group F over S, or rather over R. In this lemma, I already skipped the little step of just base changing from R to S, okay? So I'm assuming that R equals S. What really is important is the PD thickening. So let F and F prime and F double prime be two liftings of this F to T, and let phi be any morphism which does not necessarily respect the group operation. So this simply means, right, if F prime is given in coordinates which I call X, or X1 up to XD, and F double prime, and F prime in coordinates which I call Y, Y1 up to YD. This simply means that you express the Y's in terms of the X's as power series. That's all. You can always cook up such a morphism, many. And I want it to be a morphism, I want the power series not to have a constant term. Okay, that's the only restriction. I want the 0 to go to 0 so that I can substitute and work with them. And then it induces, of course, by general nonsense, pullback on differential forms. But the key point is that it preserves the invariance under the group law. Okay, modulo the exact forms. So it does give you a map on H1 de F double prime to H1 de F prime. That's the first step. So the thing to prove is not that it exists. Existence is rather trivial, but the fact to prove is that it preserves the group law so that it really maps H1 de to H1 de. Secondly, it's independent of this map phi. So you get a canonical identification of this H1 de. And this already says, in view of the identification that we had of H1 de of the lift with this guy that's here on the blackboard, okay? So remember, this was the way we wanted to define this. We wanted to lift the formal group to here, then take the Lie algebra of the universal vectorial extension, but that was via the identifications that we just made, this de Rham cohomology. So this already means that this gadget is defined independently of the lift, well defined. And then the last thing that I have to convince you is that if we have a map, which this time would be a map of p-divisible groups, or rather formal p-divisible groups between F1 and F2 over S, it would induce a map on these crystals that again would be a homomorphism and will be independent of the way you lift. So if you want 1 and 2 are a special case of 3 where the map phi 0 is the identity. And I will only prove a little part of this. I will just prove part 2, that this map phi star is independent of phi, but what goes into that proof goes into the other parts with different diagrams. And let's do it when dimension is 1, so we'll, just for simplicity, we have only one variable. So let's start with eta, and as usual, write it as df. Because it is closed by the Poincare lemma, you can write it as df over t1 over p if you introduce denominators. And let I be, as usual, the kernel of the PD thickenings. And let phi1 and phi2 be these two liftings of the identity mod I. So they're simply given as power series in Y, and as I said, they have no constant term. They're given by power series that map 0 to 0, and they're liftings. They're congruent mod I. And simply use the Taylor formula. What is the pullback? The pullback of this eta differential form by phi2 minus the pullback by phi1. Eta was the f, so this is d of the pullback of the difference of the pullbacks of f, and then you use the Taylor formula, so you get all the derivatives of f evaluated at phi1 times phi2 minus phi1 to the n over n factorial, right? These are power series that you can substitute because they have no constant term. And observe that f itself disappeared Okay? Only terms with n equal 1 show up. However, f itself had denominators, but f prime, f double prime, etc. already have no denominators, because f prime already gave you eta, and eta had no denominators. So these do not have denominators. Okay, you might worry about denominators coming from here, but here comes the divided power structure. Phi2 minus Phi1 is in I, and I to the n over n factorial is in I. So thanks to these two facts, all that is in these brackets is integral. And this is d of something integral, so this is something exact. So the class in H1 de Rham of the difference is 0, and therefore we've proved what we want. So this explains what we mean by the crystalline property. It explains the role of divided powers. It shows the relation to the Rham cohomology. And I should warn you that if you try to apply the same logic to the Hodge filtration, this is blatantly false. Okay, and this is the whole point. It's the crystal in the middle of the exact sequence that is only dependent on the reduction, but the Hodge filtration, really the translation invariant forms themselves are not independent. So now that we've more or less gone through a very quick tour of, it's not crystalline cohomology, but this is the birth of crystalline cohomology, because of course the crystalline Dunet module relates to crystalline cohomology just as the usual Eladic Tate module relates to Eladic cohomology. Yeah, questions? Sorry, yes. Yeah. The general dimensional case is just putting underlines under everything for multivariables. You can find it in Katz's article. No difference. Yeah. Where we really need a difference or something to do is where you have torsion and you start to work with divided powers and all that. Okay. So now we can recover the classical Dieudonné modules. So if K is a perfect field of characteristic P, W its Witt vectors as usual, sigma the Frobenius automorphism, and G a p-divisible group over this perfect field that you can take to be Fp bar. Its Dieudonné module, the classical one that was discovered by Manin and Dieudonné long before all this, is simply the Grothendieck Messing crystal, not of G, but rather of its Cartier dual. This is just a historical accident, okay? Some people want to work covariantly, some people contravariantly. It's very confusing for people working in the field, but don't pay much attention to this. But evaluate it on what? Okay, so what is the PD thickening? The PD thickening, or pro-PD thickening, is W2K. And I should say that the kernel here is PW, and PW always has PD structure, divided power structures, because P to the n over n factorial is divisible by P. There's a little problem with P equals 2. When P is 2, it's not a nilpotent divided power structure, but that's something that you can go around it. Okay. So this is a contravariant construction. It gives you a free W module of rank H, something beautiful functorially in this G. And our goal is to show or to explain how it classifies all these G's. So since we are over a field in characteristic P, and everything depends only functorially, remember, only on G over K, not on how you lift it to the Witt vectors, you have the Frobenius and the Verschiebung that we have discussed in the first lecture as isogenies in characteristic P. So by functoriality of M, you get Frobenius and Verschiebung as sigma linear and sigma inverse linear endomorphisms on this W module, and they satisfy the same relation that the geometric Frobenius and Verschiebung satisfy, that F composed with V is V composed with F is multiplication by P. Now such an object will be called an F crystal. So an F crystal, I did not write down the definition, but it's a free W module of finite rank, which I always call H in honor of the height of the group, with a sigma linear endomorphism F and a sigma inverse linear endomorphism V, satisfying F composed with V is V composed with F is P. Of course, knowing F determines V, but it's not enough to give F, because the image of F has to contain P times the crystal in order to be able to define a V integrally. And these objects form a nice additive category, and the beautiful theorem of Dieudonné and Manin is that this functor is an anti-equivalence between the category of p-divisible groups over our perfect field K. Mind you, I do not assume here that K is algebraically closed, okay? So remember that previously when we talked about the uniqueness of one-dimensional formal group of a given height of an algebraically closed field, we assumed that it was algebraically closed, but this is quite an interesting category, and it gives an anti-equivalence between that category and the category of F crystals. It can be enhanced actually to include even finite flat group schemes and torsion objects, but let's not discuss it. So since it gives an equivalence of category, you should be able to read certain things like the cotangent space from the Dieudonné module, and there are formulas. I should say that the original definition was not this. The original definition was taking an object that was called the co-Witt vectors. I don't know if we will discuss them in the lectures on Witt vectors. And an object that takes the role of Q mod Z in Pontryagin duality. Okay, in Pontryagin duality, you somehow use Q mod Z. Here it's some universal object that you take Homs into it, you get a linear object, and this is enough to classify they're rich enough. Actually, there was a historical twist here. It was almost enough. Then Fontaine came with what he called unipotent co-Witt vectors, but to really finish the job. But this is not the approach that we've taken, but that was the historical approach. Now you can ask to classify p-divisible groups only up to isogeny. Remember when we talked about p-divisible groups, we talked about quasi-isogenies, and we emphasized the importance of this rather simpler category of p-divisible groups only up to isogeny. What would classify them? And the answer is pretty obvious. Just invert P. And when you invert P, you get an object that's called an F-isocrystal. So an F-isocrystal is a vector space this time over W invert P that I call N of finite dimension, with F and V as above, invertible sigma and sigma inverse linear operators that satisfy F composed with V is P is V composed with F. Now, not every F isocrystal comes by inverting P from an isocrystal. From an F crystal, sorry. Not every F isocrystal comes by inverting P from an F crystal. You can take whatever F crystal you started with and just change F by F over P to the 100, and you will lose the fact that it preserves a lattice, okay? Because it has to preserve a lattice. If you divide by P to the 100, you lost the lattice, and maybe there's no other lattice that it preserves. So the theorem is that there is an equivalence of categories, and it's easily deducible from the previous one, between p-divisible groups up to isogeny and those F isocrystals containing an invariant F crystal. And we will now see what it means, but before, let me give you the standard example that will play a very important role, I think, not only in my talk, but in any other talk that will now discuss vector bundles on the Fark-Fontaine curve, for example, or whatever. You take a rational number, lambda, and you write it as R over S in reduced terms, which means that S is positive and R and S are relatively prime. And you take the free vector space, well, the vector space, oh, they're all free, over W1 over P with basis E1 up to Es, and you let F act in the following way on the basis. Of course, the extension should be sigma linear and not linear. It pushes the EIs one step, E1 to E2, E2 to E3, etc. And when you complete the cycle, it pushes ES to E1, but also multiplies it by P to the R. Okay, that's a very nice example, and you call this lambda the Frobenius slope of this F isocrystal. And here's the theorem. Now K is not just perfect. Now K is algebraically closed. The category of F, and this is due to N-Manin, the category of F isocrystals over an algebraically closed field of characteristic P is semi-simple. Okay, every object is the direct sum of simple objects, finally many simple objects. And the simple objects are exactly these n lambdas. They are just indexed by the rational numbers. For every rational number, there is this n lambda. They are not isomorphic as F isocrystals if lambda 1 is not lambda 2. And when is such an F isocrystal, and the lambdas that appear in a decomposition of an arbitrary element of this category as a direct sum of such n lambdas, of course, there could be multiplicities, they could repeat. The lambdas that appear are called the slopes of the F crystal. And when is an F crystal, sorry, an F isocrystal, when is an F isocrystal coming from an F crystal by inverting P? When does it contain an F crystal as a lattice? If and only if all the slopes are in the interval 0 to 1. Yes? R is 0 is perfectly good. That would correspond to QP over ZP. Yeah.
But then you wanted S is 1.
Yes. 0 and 1 are relatively prime.
Yeah, but also 0 and 2. But you don't want S equal 2.
No, 0 and 2 are not relatively prime. The GCD of 0 and 2 is 2. It's not 1. I'm teaching this for first-year undergraduates this year. Okay. Okay. So, fine. So, what are the endomorphisms? That's very interesting. The endomorphisms of n lambda are the division ring over QP with invariant minus lambda. Some places have a mistake and call and say it's lambda, it's minus lambda. In the Lubin-Tate case, lambda was 1 over h. Now you may ask, I just told you yesterday or the day before that the endomorphism algebra of the Lubin-Tate case is d lambda. Why is the endomorphism algebra of its d minus lambda? Because we use the contravariant construction. Okay, so if you want it to be really a covariant thing, okay, this endomorphism algebra is not commutative, so you should take the opposite. The opposite of d minus lambda is d lambda. Okay, and let's skip this exercise. And let me only say that if K is perfect and not algebraically closed, what do we still get from this decomposition? It's not true anymore that the category is semi-simple, but you still have a direct sum decomposition into isoclinic subspaces, n lambda. Okay, but the n lambdas need not be just this former n lambda to some power. Okay? There could be now things that come from the fact that K is perfect but not algebraically closed. And I think, Kiran, will you be talking about Gauss norms and Newton polygons?
Yeah.
Tomorrow. Okay, good. So the notion of Newton polygon will show up. I think it hasn't shown up yet. We will simply assign to such an F isocrystal a Newton polygon by numbering the lambdas, the slopes that appear with multiplicities, or listing them with multiplicities, and drawing this polygon where you have the first slope, the second slope, which might be the same as the first, lambda 3, and so on, and the horizontal lengths are the rank of the corresponding isoclinic part. So it's very easy to see, it's just numerology, that the breakpoints are in z squared. So yeah, well, if I put horizontal length 1, I have to repeat r over s times. Okay, or you put once r over s, but with horizontal length s, it's the same. Okay, so I finished my third talk, but that's okay, because most of my fourth talk hopefully will be done by others. So let me just say what I intend to do tomorrow, and do the very beginning, in the remaining 10 minutes, do the very beginning of the third talk. So we have seen yesterday and today 2 crystalline type constructions, okay? The universal vectorial extension, I repeat, was for infinitesimal, or sorry, any nilpotent thickenings. Definitely, it goes well for PD thickenings. This is just putting more restrictions. The Grothendieck-Messing was in the PD category. And I want to relate the 2 constructions. So I will show you now a very nice big diagram, I call it a big diagram, that will have both constructions related via a map that's called the quasi-logarithm. And this map will be very, very similar to the map that Colmez introduced, that Denis showed us before, except that Colmez did it with the crystalline periods. I will only apply it with the Hodge-Tate periods. It can be done with the crystalline periods as well, but it's the same principle and the same congruences that prove the existence of such a map. I also want to say a spoiler, so let me right away show you the big diagram. Here it is. I will go over it slowly, but I want to say a spoiler that this big map will appear in the last talk, in the 5th talk, from the point of view of the Fark-Fontaine curve in the following way. We will have a curve, okay, quote unquote, it's not finite type over a field, but it is a curve, and we will have a short exact sequence of sheaves on this curve. The first 2 terms will be vector bundles, and the last one will be a skyscraper sheaf. So it will be what's called a modification of vector bundles. Nevertheless, it's a short exact sequence. And then you can do 2 things with it. You can take global sections, or you can take fiber at the interesting point where this skyscraper sheaf is supported. So I already tell you that taking global sections will reproduce this part. Taking fiber at the point that will be called infinity, here, on that level, on the additive level, will give you this thing, and the map that goes this way will be the map global sections going to the fiber. Okay, every global section, of course, at any point gives you something in the fiber. So this is very recent, okay, this is something beautiful that ties up all these constructions and also the 2 period maps about which I will talk tomorrow. So let me just go over this diagram slowly, and to become acquainted with it, let's agree that this is a box. Okay, I am very bad at drawing diagrams in tech, but this was done in Lich. But anyhow, this is a box. The one that's in boldface is the front side, do you agree? And the one that is not in boldface is the back side. And there's also a top and a bottom, okay? So before getting into what there is, the top maps to the bottom always through log. Okay, so the top will be usually groups. Sometimes the groups will be vector spaces themselves, but will be groups. The bottom will only be modules or vector spaces, and the top will map to the bottom via log. The front side is what's related to the universal vectorial extension construction, universal covering construction, tend to say wrong words, universal covering construction, the thing that I did yesterday, the backside will be related to the universal vectorial extension and the Lie algebra of the universal vectorial extension and all that we did today. So let's go over it. Here we simply have the universal covering. Oh, okay, so I should say, there is, as always, there's R and S. R is the ground ring, and S is a PD nilpotent or pro-nilpotent, rather, thickening. Okay? I want it to be pro-nilpotent because I want to assume at a certain point when I talk about Lie algebras and logarithms that I can invert P. And I have another technical condition, but the key example that you should bear in mind is S being OC, the integers of CP, and R being OC over P. Not FP bar, but OC over P with lots of nilpotents. And we start with G0 over R and we lift it to G over S. And as we just remarked, both the universal covering and the crystal Mg have this crystalline nature. So they both only depend functorially on G naught. That's why the terms in the middle of this diagram are indexed by G naught, although really to construct them you always have to use some lifting like this G. Okay, so let's start here. We have the universal covering. In it, we observed is embedded the Tate module. This is the compatible sequences under multiplication by P that end with 0. And, of course, if you project to the 0th coordinate, then you get an element in GS. This need not be surjective. Maybe you cannot extract Pth roots from this element, but in good cases like S equals OC, you will be able. And we have the Lie algebra. So this is already a QP vector space, so we retain it. Here we take the Lie algebra of G and invert P, tensor with Q. And here we invert P, and we get the same exact sequence here. Okay, so what have we done? We have taken this exact sequence of projecting the 0th component and then taking log. So remember, this was the operator that I called theta that will be related to the theta that appeared many times before this week. Okay, so this theta is project to the 0th coordinate and take the logarithm to the Lie algebra. Now, how about the back side? The back side starts with what we constructed today, the universal vectorial extension mapping to G with a kernel which is this vector group, and the Lie algebra, the vector group remains itself. This is replaced by the crystal, and this is replaced by the Lie algebra. Okay, again, this is dimension H, dimension D, and dimension D of dual, H minus D of G. And the key map is this map that I'm going to call SG. And it goes like this. You take an element here, you represent it by a sequence. Let's write it on the blackboard. It's written on the next slide, but I want this slide to stay here. So let's take an element in G tilde S, which is the same as G0 tilde. So let's write it by X0, X1, and so on. And then let Cn, so all the x's are elements of GS. Let Cn be in EGS, in the universal vectorial extension, let it map to Xn. And then it can be easily seen that P to the n, Cn, converges to some element that I want to call S of X, as n goes to infinity. This is exactly the construction that Denis was doing, but he was using bcris plus. Here I'm doing it, so to speak, on this level. Actually, you can take bcris plus to be, or rather, acris to be a universal PD thickening of OC mod P. That's why it appears really in this theory so much. And the reason that this converges is very simple, because you see, suppose you, well, let's see why it's independent of the lifting. Suppose Xi prime and Xi were the same liftings at level n. Then the difference was in here, okay? But when you multiply it by p to the n, the lifting is in p to the n, this difference is in p to the n times this. But S is p-adic, and this is free of finite rank over S, so, or locally free of finite rank over S, so multiplying by p to the n sends it closer and closer to 0, and in the limit sends the difference to 0. And the same argument tells you why this converges. So this is the map SG, and all the other maps are derived from it. The map quasi-log is, well, here you get the same thing, so it simply apply this SG and then take the log. Okay, for this you have, of course, to assume that S is ZP flat, no P torsion, so that you can write logarithms. They need denominators. The map here is simply log, this is identity. And alpha G is simply SG restricted to TPG. Okay, so if you take element in TBG and do SG, then when you go to GS, you can go this way, so you should get 0, so it should be in the kernel, so you should land in here. And actually, it has the following description, which is independent of this SG. You can take X in TPG, so you view each coordinate xn as a p to the n torsion of GS, but this is a homomorphism from the dual to GM, from the Cartier dual to GM. They are compatible because multiplication by P here translates here to, well, its dual is the injection of the P to the n torsion on the dual to the P to the n plus 1 torsion. Okay, so they give you compatible things here, so you can take, so to speak, the differential of these things and get a map on the Lie algebra level from the Lie algebra of G hat to the Lie algebra of Gm, which is Ga, the additive group, which is nothing but omega G hat. And all the other definitions I gave you. So going back, I only want to end with, there was no ring, right? But I'm over time. Yeah, okay, I'm over time, so I should finish. I should tell you the following. This map alpha G is part of the Hodge-Tate exact sequence, okay? So we will see it tomorrow as part of the Hodge-Tate period map. This map theta is somehow responsible for the Grothendieck-Messing period. So the two periods are somehow hidden already in this big diagram. But we have to say a few more words to describe these period maps, and especially to describe their image and their nature, which is transcendental. So this will be the topic of tomorrow, tomorrow I hope to finish with the two period maps, so that in the last talk I will be able to connect everything to the Farg-Fontaine curve. Okay, thank you very much.